Okay, so next we'll talk about how our brains categorize speech sounds into some kind of meaningful categories. And in order to be able to talk about this question, we'll first have to meet the phoneme. So when a comprehender of language is hearing their language, what is it that they're really doing? Well, fundamentally, the job of the listener is to map sound to meaning. That's what your brain is trying to accomplish. So that requires converting this raw signal that arrives in your ear into the kinds of representations that can make contact with meaning. So representations that you can kind of connect to semantic representations. So here we have a little picture, raw signal coming into the ear. And then as we've discussed, it goes from the ear to the cortex. And then somehow on the basis of that signal, if the auditory signal was something like cat, you are going to find the concept of cat and you're going to be able to activate that meaning. So that seems like magic. How can that even work? So in order to do that, we need to have some understanding of the format of the sound representations that then make contact with meaning. So now we're going to ask the question, what is that format? What are those sound representations like? So in order to be able to store a representation that is useful for connecting to meaning, you want to be able to abstract away from a lot of the physical variance in the signal. So for example, if I have a stored representation of cat, so the sound cat, I don't want that sound representation to be, say, in the voice of any specific person. I don't want it to be my husband saying cat or something like that. I don't want it to be a specific loudness or a specific pitch. It should be the kind of representation that I can get to no matter how that word is said in my environment. So that's the trick. So these representations need to abstract away from all this physical variance, and there's lots of different types of physical variance. So loudness, pitch, speaker identity, accent, obviously, and other variants in pronunciation, and the list goes on and on. And so now, this is an example of categorization. So you have to take this variable input and categorize it into a more abstract category. So nothing magical going on here. It's just an example of categorization of the sort that we do all the time for all different types of stimuli. So it's a fundamental process that our brains are constantly doing in lots of different domains. So we can ask, what makes a chair a chair? Here's a very typical chair, but then there are lots of other types of chairs that we still think of as chairs, even if we can kind of mess around with a lot of the features of the chair. And still we kind of like, okay, that is some kind of a chair, okay? So now here I'm not going to talk about categorization of chairs, but rather we're interested in the categorization of speech sounds. So what makes a T sound? We can ask that question from the perspective of the listener. So you get the auditory stimulation. You know, what are the properties of that sound that make you categorize that sound as a T? We can, of course, ask it from the perspective of the speaker as well. What is it that distinguishes a T sound for the purpose of articulation from other types of sounds? In this module, we're going to be discussing this from the point of the comprehender, so and not really the production side of things. And in order to make the question a little bit simpler, I will further narrow it down. So we're going to be asking, what makes a T as opposed to a D? Okay. So in linguistics, we have elaborate theories about exactly what are the features of sounds that distinguish sound categories. And so here I have a list of those kinds of features for the sounds T and D, ta and da. Okay, so let's look at them a little bit. So first we have so-called major class features, plus consonantal, minus sonorant, minus syllabic. You don't need to worry about the details of these features. All I want you to know is that the major class features sort of talk about the role of that kind of sound in a syllable. So a syllable has an onset, a nucleus, and a coda. So in cat, k is the onset, is the nucleus, and ta is the coda. What these major class features are telling us that these are not sounds that can be in the nucleus of a syllable. Rather, they occupy the onset or the coda positions. Okay. Then the manner features tell us something about the way the sound is articulated. Okay, so for example, when we say a sound is minus nasal, what we mean is that when we're producing that sound, air is not flowing through the mouth. I'm sorry, air is not flowing through the nose. So it's minus nasal. Air is flowing through the oral cavity. When we're producing nasal sounds like and the air is actually coming out of the nose. So those are plus nasal. Then we have so-called laryngeal features. And we'll talk a lot more about that in a sec. That will be our focus in this video. And so those pertain to the kind of position of your larynx while you're articulating the sound. And then finally, we have place of articulation. So that tells us something about the place in the mouth where the sound is articulated. So a plus anterior sound is articulated toward the front of the mouth. So ta and da are both plus anterior because you make those sounds by creating a closure with your tongue and the kind of the front of your palate. Okay. Okay, so I said we're going to be focusing on the laryngeal features of voicing, and so the reason for that is because ta and da are actually the same sound in all other respects, except when it comes to this laryngeal feature of voicing. So as you can see here, ta is minus voiced and da is plus voiced. So what do we mean by that? Okay, so here is the human vocal tract, okay? So we're seeing the oral cavity here, the nasal cavity here, and down here is your larynx and your vocal folds. So now, when a sound is plus voiced, so a voiced sound, we produce those sounds by closing the vocal folds together sufficiently such that when the air passes through, the vocal folds vibrate. Okay, and we can feel that very clearly when we produce a voiced sound. Like for example, z, the sound z, like in a zoo, is a voiced sound. So you can put your fingers on your vocal folds and very clearly feel the vibration. So do it with me. Zzz. Should be a totally obvious sensation. And now if we turn that feature off, we make it voiceless, minus voiced. We get an S. So S is now the same sound as Z, except it's just the voiceless version of that. So we're going to give, we're going to separate the vocal folds a little bit more and let more air come out. And now the vibration goes away. So S as in sip or something like that, but just let it go for a while. No vibration. Okay, so that's what voicing is, sort of physiologically. Okay, but so now the example that I just gave you does not immediately make any sense given the ta-da contrast, because we can't put our fingers on our vocal folds and hear the vibration of the voiced duh, because when you're saying duh, there's actually no sound coming out at all. So ta and da are so-called stop consonants. That's because there's this total closure that doesn't actually make any sound until you release it. And the feature of voicing works a little bit differently for these sounds. So there's a bunch of these. So in English, we have pa, ta, ka, ba, da, ga. Okay, so producing these sounds is done by causing a complete closure of the vocal tract, and then you release it. So you can't hear these sounds until the release has happened. But now, after you release these sounds, there's usually vowels starting, okay? And vowels are always voiced, okay? So ooh, e, they all cause that vibration in your vocal folds. And when we're talking about voicing and stop consonants, we're actually talking about exactly how quickly the voicing of the subsequent vowel starts. So that's like the voicing that we're really talking about. So if we release the closure really quickly, then the voicing of the vowel also will start quickly. That's when the stop consonant is voiced. So stop consonant is voiced if we start hearing the voicing of the next sound in a sentence quickly. But if we don't hear it for a while, a longer time passes, then it's voiceless. So really the difference between da and ta is that the onset of the voicing of the following vowel just takes longer for ta than for da. And so now in the way we talk about the kind of acoustic feature of voicing for stop consonants is in terms of voice onset time. So it should be now very transparent. It's transparent terminology given that what we just talked about. So VOT directly refers to the time it takes for the voicing of the vowel to start. And voicing here refers to the vibration of the vocal folds. And so now here we can look at a continuum of VOT, okay? So all of these sounds are either ta or da, and I am increasing VOT in 10 millisecond chunks. So here's the shortest one. And so now I want you to listen to this and ask yourself, when does my percept change? At some point, you should start hearing a ta instead of a da. So given what we just said, so this here's you see the length of the closure, and then the voicing starts. The start of the vowel is delayed in each case, at some point you should start hearing the next sound. So let's hear. And what I was going to say, so the short VOT is the voiced sound. So we're going to start with what should be kind of a clear D, but then by the end of it, we should be clearly hearing a D. Okay, I know the sound quality is not terrific, so these audio demos are a little tricky. Okay, let's try. Okay, so now the boundary for English speakers is around here, around 30 milliseconds. And so if English is your native language, most likely that's where you felt like the percept started to shift. Okay. So phonological perception, phoneme perception, is an example of categorical perception. And here I'm showing you the typical S-curve of categorical perception. So what do we mean by that? So when we're perceiving categorically, performance is equivalent when you're within the category. So here, what we're looking at data from a classic study by Imus and Corbett from 73, where participants were listening to synthesized sounds where the VOT was increasing in equal steps, just like in the demo. And the listener has to say, is that a da or a ta? And here on the y-axis, we're seeing percentage of da responses, okay? And so now the short VOTs are on the left here. So these are all the kind of short ones. I just told you that the perceptual boundary is about 30 milliseconds in English, so it's around here. So here, their accuracy is 100% no matter what the VOT is. So what you want to pay attention to is that here, when it's like a really, really short VOT, and here when it's quite a bit longer, there's no difference in performance. Those are all the same. They're just tokens of D. You don't really hear the difference. Performance is the same. Then you get to the boundary, and there's a lot of uncertainty. That's where the performance kind of shifts. But then when we go to the longer VOTs, again, your performance is equivalent. Okay, so now you can kind of think back to the chair. Some of the chairs were like really typical chairs, and then others were like kind of more questionable ones. So here, you know, even like the middle, really typical, the most typical T is perceived pretty similarly to all the other ones. And here you would have like that maybe, you know, completely armless, legless, you know, some really funky chair here in the middle. Okay. So within category, differences are pretty, you know, just not really perceived. Okay, so just to reiterate, so that's my D category, that's my T category. Within category, discrimination is poor, so you don't really hear those differences. And so now here I'm showing you adult data. So this is how, you know, your typical adult participant would perform. So you kind of want to ask, well, how do our brains get this way? Where does this performance come from? And like, what is it good for? And so here, kind of what you want to just be aware of is that a change within the VOTs that are within category. So all of these guys for D and all of these guys for T is never associated with a change in meaning in English. So if I say, you know, like let's just say talk with a really long VOT and tuck with a slightly shorter one, it just means exactly the same thing. So if you're the ability to discriminate between like VOTs of 10 and 20 within the D category or 60 or 70 within the T category isn't helpful for understanding English. Like that, those distinctions don't matter in English if that happens to be your language. So during language development, the child's brain kind of figures out what are the meaningful categories of sounds. And by meaningful, I mean like if you swap one sound for another one, it can actually mean a different thing within a word. And so that's the kind of critical component of these categories. Okay, so now we have met the phoneme, which is a category of sounds. It's a mental abstraction over a group of sounds within which interchanging one token for another can never induce a change in meaning. And so in English, if you go from t to da, that can change the meaning of a word. So therefore, T and D are distinct phonemes in English. And if a particular distinction can cause a difference in meaning within a language, like for example in English, if we change the voicing parameter, that can change the meaning of a word. We call that distinction a phonemic distinction. So voicing is phonemic in English. So duck and tuck mean different things. Zip and sip mean different things. But if this feature was not phonemic in English, these phonological strings could not mean different things. There are lots of phonetic features that are not phonemic in English. So for example, length. The length of a sound is something that is phonemic in some languages, but just isn't in English. So for example, so here's, you know, if you like lengthen the of duck, duck, it still means duck. You know, that does not have the potential to have some other meaning in English. Just kind of a slower duck. But in a language like Finnish, for example, happens to be my native language, length is phonemic. So you absolutely have to pay very close attention to length, and it's very easy for Finnish speakers because they hear it really well. It matters in that language. So here's an example. So tuli means fire. Lengthen that u and you get tuuli. Well, that means wind. Different thing. Got to pay attention. We can also lengthen the L and get yet another word. I guess you thought that would be earth, wind, and fire. But it's customs. So tuli means customs. Okay. Very important. Very different. Okay. So that is what it means to be a phonemic feature in a language. Can cause a change in meaning. Okay, so going back to that original question. So what is the format of the representations in our brain such that those representations are abstract representations and can connect with meaning? Well, we think of them as sequences of phonemes.